Look at the previous video for the details of this setup. I'm starting with a low noise oscillator from Ventsa, sending the signal through this box, which is a crystal filter with many crystals on 10 MHz. It's similar to the filters I'm using in the low noise oscillators, these ones, and you can see about them in early versions of this Nerds series. And I'm evaluating the noise, sideband noise now, of the signal that has passed through the filter with Linrad. I have collected 55,000 averages now, and I created a small impulse noise here while lifting and putting back that filter. But the channel levels, they are like this, and the correlation is 11.7. I was running at a frequency separation of 35 Hz, and I have now changed it to 100 Hz and start collecting, keeping the correlation information from the spectrum here. And I will wait for a while to get better statistics from this. The correlation advantage is 8 dB at many averages, 67,000, and channel levels 135.3 minus and minus 136.7. This is a separation of 200 Hz. The channel levels minus 136.9 and minus 137.8, and that's with 74,700 averages, and the correlation advantage 15 dB. This is a 500 Hz separation, 147,000 averages, and 20.3 for the correlation advantage. And here are the channel levels. I'm collecting averages now with 3,268 FFT size for the first FFT. And note here the 50 Hz modulation spurs suddenly increased dramatically. The reason is that I switched on the kitchen stove. It's 1.5 kilowatt and it's boiling water at the moment. I switch it off. And now I'm back at the computer. The kitchen stove is about 18 meters from where I have my experiment, but the magnetic field it generates is fairly large at this place. And I have seen previously that this spur varies a little bit up and down in a way that I didn't understand and really didn't worry about either. But now I have a better explanation. 50 Hz is around and it's causing modulation because of the nickel in the BNC connectors, as I have established earlier. I'm now looking at 40 Hz offset. And you can see on the curve, the correlation curve is very noisy up here and it's far below the white track. But here at around 50 Hz offset, the curve is not noisy at all, and it is not so far away from the normal average spectrum. So this means I'm seeing something extra noise here from the crystal filter. And I'm measuring now at 40 Hz offset. I did look at 5 Hz previously here, but the number of averages was not large enough. So I switched to 40 Hz and evaluate the noise floor here. I have to wait for it to come back. And this is what I see, 137.0 and 141.4 minus. And the correlation advantage is 10.3 as at 47,400 averages. This is 100, and I read out the levels of the channels, 144.4 and 146.6. And the number of averages is 57,800, and the correlation advantage 11.2. This is 20 Hz separation. The channel levels 127.1 and 134.7. This is 68,400 averages, and the correlation advantage is 13.4 dB. This is 10 Hz. It's been a lot of time. So now I have 116,500, and the correlation advantage is 17.2. And the channel levels minus 116.4 and minus 125.7. Frequency separation now 5 Hz, 192,000 averages, 18.8 dB correlation advantage, and 108.5 and 110.8 is the channel levels, and with minus signs, of course. I have fed the numbers of the study that you have seen up to this point into my spreadsheet program. You can see the details of it in the previous video. So these are the sideband noise levels that I have established for the vent cell oscillator, followed by this high power crystal filter. I have made measurements on this filter with the interferometer in this video, nerds46. It's here, and it starts like this. This is a high power crystal filter for 10 megahertz. I have made it because I want to look at what would be the flicker noise from the crystals in an arrangement like this. I have plotted the results from this measurement. It's the red dots here, and they form a straight line with a slope consistent with flicker noise. Now it bends down here. It does go a little bit below the vent cell because it is a filter we have, so it suppresses the noise of the vent cell oscillator, which is the green points, and it goes like this. And here at small frequency separations it cannot go below the vent cell because we have no filter action very close to the center. So extrapolating the straight line, it comes a little bit below, but it has to bend off and follow the vent cell line. The interesting thing is that the interferometric study gave the same straight line. So it was not, as I was afraid of, a problem to study in the interferometer. I was thinking perhaps that the crystal that provide a very fast change of phase with frequency, when balanced perfect for the carrier, it might be less well balanced for the noise sidebands of the oscillator used. But that was not the reason for the noise I was seeing. Now, the noise of the crystals, and these are 30 crystals in parallel, so the noise is significantly lower than the noise from a single crystal. 30 crystals in parallel, they give flicker noise that is uncorrelated. It means that the noise from a single crystal should be square root of 30 times lower. That's 7.5 dB. So a single crystal should have a line that is 7.5 decibel higher and parallel here. Now, that is if all crystals are equal. So that's what I'm going to look at next. What is the noise from single crystals? Here is a filter with a single crystal. It behaves like this: 50 ohms and 0.8 dB loss. This is a little bit surprising. One should have expected an impedance a little bit higher than 50 ohms, because there is a serious impedance in the crystal. But I have a short here, and I place that. On the output of the filter, and now we see that the serious impedance in the crystal is only 9 ohms. So it's a high Q crystal. The vent cell oscillator gives plus 12 dBm, that's 16 milliwatts, or 18 milliamps and 0.89 volts. So in 9 ohms, the power dissipated will be 2.9 milliwatts for 18 milliamps. That's a bit too much. I will insert a 6 dB attenuator to bring the power below 0 dBm for this crystal, and also for crystals that have a little bit higher series resistance. I have set the bandwidth of 10 Hz and verified calibration. Of course, I had to recalibrate with a different signal level, but now it shows 0 when I'm on the center of the signal. And I go 100 Hz away from here, 62.25 means 63.25. That's here. And here I have the noise floor in the 2 channels. Well, when I change the frequency, I get a glitch like that. And I have to clear the correlation averaging, that's alternate Z. And then just wait. Now I have collected 13,000 averages. The correlation advantage is 9.7. And channel levels minus 132.7 and minus 133.7. This is another crystal. You can see the green and yellow tracks are closer to the white now. the correlation advantage is 7.0 dB, and the channel levels are 133.4 and 134.2. This is a particularly good crystal. 9200 averages, 12.5 dB correlation advantage, and 134 and 135 minus for the two channels. Here is a particularly bad crystal. Correlation is insignificant. I can read the channel levels here. Minus 106, and both channels are the same because the noise comes from the crystal and it's the same in both channels. This is the bad one. Here is the result of the evaluation of these data. The best crystal here is a reference. The other ones are 4 to 6 dB more noisy, and the old one is 41 dB more noisy, and I will not use that one. I'm doing measurement now at 100 Hz separation. The filter with the single crystal comes here with the best crystal. It's well above the citrine, so it is a valid measurement. The other ones, two of them here and one here and one here, they are, as noticed on the printout, significantly worse. Maybe I can find really good crystals and also maybe some really bad ones that I could sort out from further experimenting. And of course the bad one comes far outside the graph, 41 dB up.